Alrighty, happy Thursday afternoon, post-reading day. Everybody have a good reading day and day off and all that good stuff. This is the time of the term when the end is in sight and people are tired and worn out and all of that. And I've saved the best of this class for the last. And I don't know if that's on purpose or whatever. The topic that we're going to start today, we'll finish the term with. And it's the one that scares me personally. So I don't have a totally unbiased opinion about how to present it or my feelings towards it. It's called abrupt climate change. It's the notion that climate can change faster than we expect it to. And we're going to go through that. We'll have it, this is a longer lesson again, there's more days to it here. Today I'm going to start off with the concept that we can define it. We'll define it, that's fine. I will take you through a series of technical arguments. They're pretty technical and I'm not trying to impress you with a technical geek. What I'm trying to impress you with, or the message I'm trying to get across is, we've been fighting with abrupt climate changes for several decades. Nobody yet understands how to explain them. So the take-home message, if you can remember that they can't be explained or they haven't yet been satisfactorily explained. With all kinds of explanations. But I'm going to walk you through three examples and show you why they don't work. And these are kind of the leading paradigms of thinking about climate change for one particular climate event and one of the biggest warming events in the geologic record. Before I go any further, any questions where we're going today? Okay, let's do it. And we already talked about we're on a new topic. We'll finish the term with this, and that's fine. It's called abrupt climate change. I'll give you a definition a little bit. I'm going to talk about terminations. Termination, I think we've at least mentioned it before. It's the end of the last ice age. In other words, we're in an ice age world that it goes between ice ages and not ice ages. And today's climate's not the ice age, obviously. And so, the technical terms for that's a termination. And we're going to dig into some details about it with these technical papers that I'm going to go through. Because it's the example or natural example of one of the most rapid, large-scale, abrupt climate changes that we know. I'm going to walk through three hypotheses that support it. And the way I've got it formatted a little bit to help you keep organized is an overall hypothesis that'll be in big bold print. And then I'll talk about relationships, or I should have probably retitled that, factoids or findings that somebody brings to bear on the question. And so what we're going to do is, there's three hypotheses to explain this termination. We're going to spend some time looking at what they think it is, and then information that basically shows doesn't work so well. And the bottom line is that they happen fast, they're a big concern, nobody understands them. Or let's put it this way, the contentious debate is all over the map, so that means we don't understand it. Okay, working definitions. Abrupt climate change, something to do, if you're in physics, it's a transition of the climate system into a different mode on a time scale that's faster than anything than the responsible forcing. So an example, and this is totally fictitious to drive home the point, is we know that during the course of the day the sun comes up and it gets warmer and warmer, right? And so that's a pretty predictable pattern depending on the weather. But an abrupt change would be that the sun comes up, starts getting halfway through the sky, and all of a sudden it gets just up over the horizon and starts warming up, but all of a sudden you go to the maximum temperature of the day. And that would be, well, how does that happen? Because we're adding warmth, but all of a sudden it jumps what they would call a mode. So it's a nighttime mode and a daytime mode. So we could think of it as all of a sudden it was bright sunshiny and a bright night, and that's a mode, two modes. We have a smooth transition. Abrupt climate changes are not smooth. They are exactly that. And for the reason that we're concerned about it is because it's one that takes place so rapidly and unexpectedly for either human or natural systems to adapt to it? Can we respond to it? It's one thing to see a change coming and think about it and have several years to react to it. It's another when you get smacked face in it and you have to deal with it suddenly. Your planning, your ability to adjust isn't so good. Tipping points is a term that's related, not exactly the same. This is a better working definition, but this would be an example of a tipping point in the climate system. There are many examples in the past, and to keep us going, I'm going to talk about 3 of them from the termination. For the homework, the assignment, whatever we call it now, assignment for today, go find some other examples and just get them under your belt. And cause is an interesting relationship. In my view, a lot of things, I was a physics major for a while, but quantum mechanics and I didn't get along very well. But physics in general is sort of applied motion, how things work like that. And so we're always looking for a cause. Why did the glasses fall down to the table? The cause has to be gravity. So we like to think about in terms of if we see something, there has to be a reason for it. We're always thinking about a cause. So-and-so, the stock market went crazy. Well, what was the cause? We might intuitively as people, we'd like to know why something happened. If we don't know why something happened, we're unsettled about it. So if I'm going to argue, and I am going to argue, that abrupt climate change doesn't have a well-described cause, that gnashes a little bit. But I'm going to do it anyway. Okay, ready? The example I want to start with is the ice ages. And we've talked a little bit about them. They have an asymmetrical pattern. Here's time today, 400,000 years ago. Temperatures in the blue. And we start off with warm time, gets cold with some fat, it gets warm. 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 Each one of those is called the termination. And they're numbered. This is the termination that's the most recent. It's the one we've studied the most. All the examples will be from the termination. This is the warm climate that we're setting in today. This is the colder time, 6-7 degrees colder temperature-wise. The concern about predictions of warming are a few degrees, depending on how far out in the time scale you go, but it's going to be a vertical line on this scale, because that's 50,000 years. But we're talking about this as a prediction. So this is a big deal. The slope of that line has always been very sharp. And over my career, we've watched that line stay sharp. You know, it looked kind of sharp, and then we get better dating techniques, and we found it was still sharp. And then the better and better dating techniques kept it getting shorter and shorter and shorter. We're now down under 200 years. Something that's supposed to operate on tens of thousands of years, 200 years is abrupt. Okay, so we're going to go to the Ice Age. Some of the examples I'm going to draw on are from a book by a fellow named Wally Broecker, who's now deceased, but he was an eminent climate scientist who recognized this problem. You'll see one of his illustrations later in the course. But if one wanted to get his thinking on it, he wrote a bunch of textbooks. He was a geochemist, studied the oceans. You can get them online. And this is a pretty picture from Greenland. But so that's the title of his self-published book, basically. And we're interested in these terminations. And so he explains the terminations, and I'm drawing up some examples from him on that. The first hypothesis, there's going to be 3, is the notion of orbital variations. This is the kind of thing you'll see in your high school textbook. This is the thing that would have been at the museum center for a while. I don't know if they've gotten rid of it or not. But the idea that the Earth and the sun don't stay, the Earth doesn't orbit the sun in a simple fashion. And because of that, you get different amount of radiation. And you can mess around with it, but it turns out that the shape of the orbits first, turns out that we were tilted, first of all. And so sometimes the tilt is such that the solar radiation is incoming here, and other times it's incoming at an angle. So the angle changes between June and December of which way the sun's radiation's coming in. And that varies over time. And that's got a cycle of 41,000 years. The Earth warbles like a top. So it doesn't always point the same way. And that operates every 26,000 years or something like that. And that's called precession. So we've got the tilt, precession, and then the fact that the Earth goes around the sun in an ellipse, not a circle. Well, the shape of the ellipse changes a little bit. So all of those would be different things that would change the incoming solar radiation, hence climate. Because we've talked about the radiation balance being very sensitive. So if you monkey around just because of the physics that further things away are less warm, basically, you can modulate climate. So these, I don't care that we know the names of them, but the notion that the Earth's got a complex pattern could make for a complex pattern of changes in the radiation balance, the incoming solar radiation. And so there's always a bunch of little captions here of people that worked on it, because Broker liked to do that. So the conceptual idea is that you can calculate these things, and a fellow named Milankovitch did that years ago. And the point is that you can get some radiation balance, and if you do it in the northern hemisphere and the southern hemisphere, they're different. They're just flip-flopped. They're symmetrical flip-flops. Northern hemisphere, less radiation coming in, colder. In the southern hemisphere, more radiation coming in. It's the warm season. Flip-flop the warm, cold. It's just a metric, and it works on an annual scale, no problem. If we go back, and these graphs go back 300,000 years, you can see that it bounces around a little bit. Well, the natural thinking in the early 80s was these, well, before that, in fact, these orbital variations, because sun's the big deal, would explain the ice age cycles. Okay, that's fine. And it turned out there's a little bit of a glitch to this. And a fellow up at Ohio State, who actually was the same fellow that discovered Pine Island Bay could be a problem child, discovered that, geez, if we get different radiation balances, we really should have different glacial cycles in the two hemispheres. The southern hemisphere and the northern hemisphere radiation don't match, so shouldn't the glacial cycles be out of whack? And I spent about 10 years in the Lake District of Chile, halfway of it. We were testing part of that hypothesis. We were trying to find out what the glacial fluctuations looked like at that stage. And when you make the comparison to the northern hemisphere, it turns out, so you make the comparison between Chile and where we're setting and New Zealand, well, we're not quite set on this map, the glacial fluctuations all behave the same way. So that implies the orbital variations don't explain that very well. They're not that they're not part of it, they don't explain the whole story. Moreover, they couldn't ever explain that rapid change. They could, the broad pattern, but not the rapid change. So the next idea that comes along with a different host of characters is that CO2 matters. Why not? CO2 is a big deal. This graph, which we had earlier, was a very famous graph because it showed the temperature change and it showed the CO2 relationships. And boy, there was a one-to-one. When the CO2 and that's going up, the temperature is going up. The problem is these records are from different places, acquired for different means. You couldn't put them on one-to-one. So you couldn't actually tell which one was going first and which one was going second. But if you looked broadly at the CO2, which would be this one, and the sea level, and the temperature, a proxy for temperature, they looks like they match. And that's fine. And everybody's happy and we can all go home. Except for, of course, there's except for. There were folks, cast of characters here, that started looking at, wondering about precipitation patterns. not just temperature, but this precipitation. We've made a big deal about the difference between temperature and precipitation in this class. They look at, here's the last ice age, and that should be an abrupt thing, but it's not. The precipitation patterns have a rhythm. That red line's one of those orbital variations, but it's only one of them. So they follow some orbital time scale, and this is on rapid, but it doesn't explain the rapidness again. All right, so cave records, wonderful things. Ice core records, same song and dance. They have a slightly different pattern. They do pick up the termination. Dansgaard is sort of a name that works about, he worried about the oxygen isotopes as a proxy. And they're partly temperature and then this precipitation, but there were Dansgaard-Oshker events. This is what Broca liked to do, name things after predominant scientists. And the recognition from the ice cores, the very first ice cores, geez, they bounce around pretty rapidly. Then there's a termination. Well, I'm focusing on the termination, but there's a hint in here. They're sort of 1,500 years long. Okay, well, why do we have flickers in the ice record? Well, they all end abruptly. And then going back to, I don't know why that says 1, it should be 5 or 6 or something. If we look at this a little more detail, here's a temperature record. It's Southern Hemisphere, so it's different than the one you just saw. Here's the CO2 record. Here's the methane record. So maybe CO2 doesn't do it, so let's add the methane. Well, that kind of looks good, but it doesn't really match. Okay? Then the wind gave us another clue. Wind is an important proxy. We don't have a lot of things for it. Here's an ice core record of dust. Dusty, 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 really dusty, really, really dusty. No dust, no dust, no dust, 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 no dust. These dusty days, you'd have to clean your house once a month or something. The point is, they turn it on and off. It's not like it got dusty or it took 1,000 years to get dusty. It turned on and off. Off, on, off, on. Something's telling us something about this. This is an ice core. How fast can you turn the wind on and off? Well, we've talked about the intertropical convergence zone. That'll come back up and on. But maybe the wind is telling us something that we didn't see with records that were slower reacting. So the point is, when you add all of these things up, there's also multiple terminations. And they have somewhat different structures. Here's the one we're dealing with. This one's got a bump in it. This one's got a bump in it. This one doesn't have a bump in it. This one doesn't have a bump in it. So there's something system behavior that's not easily to predict. Doesn't work with Milankovitch, doesn't work with the CO2 records. So we're still searching for a cause. So to articulate this, a paper 4 or 5 years ago really made an argument that would work. Time's going the other way on this. So down here in the LGM, the squiggly things are out here someplace. Starting 18,000 years ago, let's get the colors right. This is a temperature, the red is the temperature proxy, and the blue is the CO2 level. But the argument was made that they were pretty close and they mirrored each other, so CO2 is a natural candidate. We have a mechanism for it. We have a cause. We have an thing that we can explain, and CO2 is a good character. And the way this graph is going, the CO2 went up, and then the temperature started going up. So that's all fine and consistent. Back to the ITCZ. People looking at caves were able to find out that the ITCZ position changed. And it changed in an abrupt fashion. It wasn't always in the same place. Today it's here, there it's a different place, there it's a different place. And how is that recorded? It's recorded in precipitation patterns. So again, we see some evidence that the seasonal positions change over time. Okay. I don't remember if we need to talk about that one. Oh yeah, the CO2 thing goes on and on because scientists, they like to refine things, and so someplace in, I'm not exposing you to all the literature, but there's some arguments made that the temperature reconstructions weren't exactly valid. So here's a whole group from Arizona that spent quite a bit of time making a better temperature reconstruction. And so this is, no, this is at the end, and then this is blown up. This is the modern day CO2, and there's the little blip that we've measured. Here's the big blip that was the end of the CO2. So they have a more refined temperature record. Oh, that's fine. So that's a useful piece of information. We'll tuck that away. The third hypothesis is a more involved in one. It's more recent. And it basically says, oh, we observe that when it gets warm, the ocean currents change. And perhaps the atmospheric changes. So to set it up, we're looking at the South Pole. We're thinking about a wind pattern that just goes, this is wind speed, temperature. Cold here in the center of the white, surprise, surprise. Here's the South American Peninsula. Here's the Southern Alps of New Zealand. And correspondingly, the wind goes around and 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 around. And that's where I spent last March and where I'm going to spend this March, down in the wind belt. But those wind belts stay the same place. There's something called the westerly winds. And are they always right at the same spot? If they're right at the same spot, that's fine. But if they move a little bit, that changes the temperature distribution. Notice how it's cold in this case, and quite a bit warmer up here. So if you change this belt of circulation and happen to be right around New Zealand, then you have a sensitive tracker. All right, but let's go down into what did they do there. They looked at glaciers. There's a shock. These are trim lines or bathtub rings of the glaciers around the edges of the lake. And another place. And then they did a dating technique to understand when all of this happened. And there's way too many details to get into here, but basically glaciers are related to temperature. So we have a different temperature proxy. So we've taken 2 or 3 different temperature proxies here. This one's really sensitive to summer temperature. And the fact that there's nice little belts of moraines there and a lake there is actually a clue. So there's moraines at the last glacial maximum in all these places, and then big lakes behind them. What they discovered, and in plotting this by temperature and time again, is rather than the signal that we kept seeing where it was gradational and sharp, it's actually cold. The glaciers were always at a certain spot. They came out and they came out and they stayed there, 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 and they went back. Again, at a very steep angle, therefore very short. And this is the one where, if you think about their dating technique and how close they can measure that rapid, abrupt change from 6.5 below, in this case, to 4.5, 2.5 below, it's less than 200 years. That's the analytical resolution of the dating technique. That doesn't say how fast it actually took place. But the glaciers were happy. They came around, came around, came around, and then they had to go be happy at a different temperature regime. And today that goes on, and we've got another warming where they're getting happy. So this is an observation made by the team that did the Zealander switch. They also looked at the ocean temperature. And this is an ocean record off New Zealand, and it's a little bit clumsy to read. But basically, this is south of New Zealand a little bit, and this is even further south. So this is north-south position, and this is time. And the pretty colors are temperature. And so what you see are warm reds and cold blues. And so if you track this over time, it's greens and blues, cold, greens and blues, cold, little bit of structure to them. So there's some places that are cold at that latitude, 50, and here, and a little bit warmer in here. But the whole thing falls apart right here. The ocean structure changes. the warm water comes in down to here where it was nowhere within, what, 4 degrees of latitude. No, 1, 2, 3, 4, 5 degrees of latitude. All right, 5 degrees of latitude, 60 miles. 60 miles per degree, so it's 5 times 60 is 350 nautical miles. That's a rather rapid jump in the ocean temperatures. And it's coincident with the jump in the air temperature. So this group pointed this out. So far, so good. Now we go back to the CO2 argument at a higher resolution. Time's going this way now. We'd like to switch back and forth. Here's their glacial mode. Here's their jump to their interglacial mode. Here's the CO2. The CO2 lags the jump. The temperature happened before the CO2 went up. How does that work? Well, it doesn't. There's no doubt that the CO2 goes up and therefore it changes its radiative forcing because it's going up in CO2, but it's not causing the temperature rise. The temperature rise is too fast for it. This is back to our operational definition. If I want so rapidly and unexpectedly, no, it's transition to a different scale is faster than responding forcing. Milankovitch, forcing was this long, too fast. CO2 responding this long, too fast. So that's why we call these abrupt climate changes. All right. Now, they also, in that particular scientific paper, went through an argument about why the structure of the atmosphere would change. And it's a modeling experiment, and it basically says how would the oceans, let's see, the atmosphere and the oceans change. The wind speeds here and the summer surface temperature. And those are anomaly maps. So the point is that they, from the modeling perspective, have a physical reason behind it. And that's too thick for us to go into now. So from the model, sea surface temperature, before and after, the model makes it work. It agrees with the geology, and then the geologic record suggests that it has to be a global impact. So the Ice Age ended rapidly. Biggest natural one we have, and the argument that I just presented was we've been fighting about it for 100 years, but we haven't agreed on it yet. All right. Let's step back and rather than me talking about it, let's ask you what questions you have. Why would you care about all that gory detail? You could ask that question. But I'm open to any questions. I'm sorry? What's the take-home message from today? At least for that one example. I highlighted a particular example, gave you 3 different reasons or causes that people like to use. So far, none of them seem to be working. Okay. What would you like to know from today? Why it happens that way? Well, yes.
Which one of the 3 do you think is most likely?
I can answer that 2 ways. Do you want A or B?
A.
Okay. A is because I know the characters involved in it, and so I trust what they're doing. The other answer is what happened? This computer hasn't been behaving very well recently. The other reason is it's actually the most recent. I mean, what I just presented was an idea over time. As the orbital thing was all the pizzazz when I was your age. And then the CO2 came in sort of 15 years ago. And now the Zealand switch came in a couple, 3 years ago. So we may not have had time for some new line of evidence to defeat it. So it's the prevailing champion, but only because somebody hasn't challenged it yet. What would you like to know? Excuse me? No questions? You have questions?
Is it possible like it could be a little bit of everything?
Could a little bit of everything be that? That's a possibility. And that's why you go to things like this, where you say CO2 could, it makes sense that it warms up. But geology is all about time. And the fact that CO2 goes up after it gets warm means it can't be much of a player there. It could reinforce the warming, but it can't trigger it. And it turns out, as they've been looking into this more and more, this is about the cold oceans actually absorb more carbon dioxide. So this is actually the carbon dioxide in the atmosphere is going up because it's coming out of the ocean, or some of it's coming out of the ocean. So that's something that when we first talked about CO2 and the atmosphere, we couldn't tell that. We couldn't tell there was a lag. We can only tell a lag with better dating. But this diagram, when it came out, was all the pizzazz of, wow, CO2 and temperature, they're perfectly phased. Well, nobody did the physics to figure out how much that warmth is. And whether that, back to our climate sensitivity, that much CO2 could actually make that much temperature change. So you can start eliminating one or two pieces of parts. It's attractive to try to kind of keep thinking of a thought. I'm going to introduce next lecture sort of a different conceptual way to look at it that would preclude us having to worry about whether it's this part and that part or the other part. All right, gentlemen, way in back. What do you need to know? I used to have a little set of cards and I have everybody's name on it and I turn them over randomly. And I'm trying to be random with my question asking here, but I should have gone back to the cards, I suppose. All right, you're going to get a break. She'd like to know something. We'll come back.
I just have a question about the homework, if that's okay.
Excuse me?
About the homework.
What about it?
So, like, the question is research.
All right, so let me put it up for everybody. The general concept is I want you to get a little more familiar with abrupt changes on different time scales.
Okay, so you're wanting, like, specific, like, events that happened, or
Yeah.
reasons why they happened?
Well, I want to know why we think they happen.
Okay.
So the idea basically is find 4 examples that people would call or have called a rapid climate change. For your searching, rapids might be a word that comes into place. And then this is the kind of information that I want for each one of these things. And I want you to just put it in the table makes it easy for me to correct it, basically. So they're all given a name. When are we talking about? And I think what you're going to find is you'll see different time scales. We just talked about a time scale from sort of 17,000 to 14,000 years ago. But I think you'll find other abrupt climate changes on different times. So when did it start and stop? Is it involved in temperature or precipitation, or both? And then everybody will have an explanation because we're driven to explain something, so they'll have a cause. It might be a little technical, but you can cut and paste the technical goop. And then be sure that I can double check where you're getting your information. Did that get to your question? Now the gentleman in back.
I don't really have a question.
You don't have a question. This is all clear as mud, right? Why am I doing this? I'm harping on this cause business.
I was just curious, is there any room to think that there could be another hypothesis, or they're pretty like set in stone? It's like this.
Say that again. I think it's a good question, but I didn't.
Do you think there's like any room that there could be another hypothesis down the line, or are they pretty set in stone, like this is what it is?
Is there any room for hypothesis? Well, I would hope so, otherwise we'd be out of a job. I mean, that's the kind of thing that some of us in neuroscience work on, and we test that hypothesis. And some of us spend most of our careers testing a hypothesis that somebody else came up with the idea. And others are the really few, like broker, are the people who put out the ideas for testing. So, I mean, figuratively, I've spent quite a bit of time testing various abrupt climate change hypotheses, but I didn't think of the cause. I'm not that smart. But could there be another hypothesis? Of course. I would expect that in 10 years we'll have a different way of looking at things, maybe even 5 years. It's going so much faster. The thinking of Milankovitch took a century to figure out. There was some glitches to it. Like I said, it was, yeah. And then each successive time between those actually is getting shorter. So there should be, by that prediction, there should be another hypothesis in a few years. Maxine, what do you got for question? Everybody, see, that's the trouble. I let one person say, no, I don't have a question, and then it just sort of cascades. Anything else I can answer for anybody? Sir?
I've got a question about the glacial, like when we were going over how the carbon is not the cause of one of the rapid changes. Do we check more than one, like, source for that?
This
One example of that?
this here?
Yeah.
Okay, so it's a very good question. This example comes from a big pile of data here in New Zealand. Took them 10 years to put that data together. It's one spot.
Okay.
So it wouldn't be surprising that there's all of a sudden a whole bunch of NSF proposals that say we're going to test this someplace else on the planet. We just put in a proposal to test it here on the Falkland Islands. Different, same latitude, but a different ocean basin. We're effectively testing this here because it's the closest thing to Antarctica. But there are the people who would be testing it in the northern hemisphere also. So, yes, the number of sites that presently support it are depressingly low. They're solid what they are, but we need to validate it before it's going to be widespread accepted.
Okay.
And it'll take, that hypothesis has been out about 3 years. That's long enough that people are writing proposals. It'll take another 3 years before their data sets come in. And so it will take, the joke in academia is it takes the retirements. In other words, you'd train a graduate student on this. I was trained on orbital parameters. Yeah, all right, so it took me a career to come around to this one. So that one might take a few years to get accepted.
Okay.
Sir?
Can we use the Younger Dryer as the one example?
That's a classic example. Most of you will come up with that as a suggested reason for the Younger Dryas, correct? And that I spent 10 years in Canada working on, testing a mechanism for that. Anything else? It's running towards the end of the term. We're all tired. We want to get, Thanksgiving's coming up. It's a challenge to keep people's attention when we have breaks and stuff. So I'm just going to say let's call it a day. Have a good weekend. We'll pick up on this on Tuesday.